Hi guys, today we're going to be doing an episode on sorting algorithms, preferably the merge method, and this is how you write it. And, so Daniel, I want you to tell me that if you had like a sequence of numbers, like, let's say you had 2, 5, 6, 8, 1, -6, 3. I want you to tell me what you would first do to sort these numbers instinctively.
Okay, so first I would probably find the smallest number, which is -6 right here,
Okay,
and then write it down.
okay.
Then from the remaining numbers, I would find the next smallest, which is 1 right here, and then write that down, and then just continue in this manner.
And what would happen if you had, like, say 20 numbers? Then what would you do?
20 numbers?
Yes. If you had,
Well, I do the same thing.
you do the same thing. You go through everything and find the smallest number.
Yeah.
Okay. And okay. So his method, he goes through everything, finds the smallest number, then finds the next smallest number. So let's analyze this method like a computer, because we will judge the efficiency of our methods based on what a computer would do. And a computer, every single time it makes one comparison, it equals one step. And to judge the efficiency of our methods, less steps equals better. So we want the least number of steps possible in our method. So based on Daniel's method, let's say the computer started from here, and it were to find the smallest number out of all of these, out of the entire sequence of numbers. So if it started right here, it would first compare 2 with 5. Then it would compare the smallest out of that, 2 and 6, and it would keep going down. And if this sequence had n elements, it would make n-1 comparisons. And you can probably see why it's true, because it keeps comparing this. And the reason it makes n-1 comparisons is because we want to base the efficiency on the worst possible case scenario of these numbers. And why do you want the worst? Well, the best possible case scenario for any type of method would be if all the numbers are already in order. So the number of steps would be 0. So to actually judge the efficiency of one of these methods, we would base it on the worst case scenario. So the worst case scenario is if like all the numbers are in backwards order. Then he would have to go all the way to the end, and that would take n-1 comparisons. Okay, so if it were in that horrible order, we would keep going down. So let's say it was let's say it was in 3, 2, 1, 0. Okay, so there's n 4 elements. Okay, so it takes 0 out after making 3 comparisons to do 3, 2, 1, and 0's over here. Now it makes 2 more. So it makes n-2 comparisons in the second step. And if you keep doing this, you can see that it eventually goes down to 1 comparison. So the total number of comparisons would be 1 plus 2 plus 3 all the way to n-1, which would be equal to, if you've ever taken if you ever learned this, would be n-1 over 2. This is equal to the sum, and you can probably find this over the internet, but based on how you're watching a math video, you probably already know this. hopefully. And so this is the number of steps it would take. Now, considering this, let's try to find a more let's try to find a more efficient method. So Daniel, let's move the rectangle a bit.
Alright.
It's okay. So get into the area. So what we have so far is n minus 1 over 2 steps. Let's try to find a method where it's less than that. And the method I'm talking about is going to be the merge method. And is this the fastest known method? No, it is not. The merge algorithm is actually takes greater steps than the heap method. And the heap method delves into more computer science. It isn't entirely practical in real life because it requires more organization. So I'm not going to go into this video. We may do it in a future video. However, the merge method only takes about like 1 or 2 steps less than the heap method. So the heap method is only slightly more efficient. So since the merge method is practical in real life, for example, if you're alphabetizing books at a friend's house, if you're doing any sort of sorting which includes an order, the merge method is actually practical. So let's see how the merge method works. So Daniel, so let's say you had 2 groups of n over 2 elements. And you want to merge this into n elements. Let's say these groups were sorted. Okay, and we want this to be sorted. So how many steps would it take to put 2 n over 2 element sequences into an n element sequence? How many steps would that take?
First, let's just use an example. We have like first sequence is 1, 2, 3, 5, 7. And the second sequence is 2, 5, 8, 9, 10. So first I would compare these two and write the smaller one down. So that's one comparison.
Okay, so I'll write the sequence. Yeah, I'll write. Don't worry, I'll take care of it.
Okay, you can write it down.
Okay.
And then after I get rid of this one, then I compare the next sequence, the next number in the sequence, with the original number. So you have a 2 and a 2. It doesn't really matter. So that's the second comparison. And then we just keep on doing comparisons like this.
Yeah, so it keeps on going.
Yeah, so and then since we got rid of 2 numbers in the since we got rid of 1 number in the first comparison, 1 number in the second comparison, and then to the last comparison, we can, after we get rid of the smaller number, we don't need to do any more comparisons. There's n minus 1 comparisons.
Yes, there are n minus 1 comparisons for n over 2 elements. I think it would be easier to explain how many steps it would take if we started from the base case, which is just 1 element, compared with 1 element. So if there are n elements, we start out with pairing up any sort of 2 elements, it doesn't matter, and we compare them. So there are n over, so in this case there are n over 2 groups of 2, and I should say you know, this base case, but it doesn't really matter because despite in some cases n not being a power 2, it still approximates most times. Like you're only going to be 1 or 2 comparisons off, so it doesn't really matter. So I guess you could write that notation if you want to do. But anyway, so we realize that since there are 2 elements in here, it takes 2 minus 1 steps So it takes 1 step to compare these. So the number of steps it would take to compare to make groups of 2 that are ordered would be n over 2, because it takes 1 step each. And for if you're comparing two groups of 2, well, you compare these two, you compare these two, and you compare these two, and you would have n over 4 groups of 4, and the number of steps it would take would be 4 minus 1 steps, which is 3 steps, and that would be n over 4 times 3, which is 3n over 4 steps. And we're beginning to see a pattern. So let's just do 4 and 4 by 4, so it's n over 8 groups of 8, and it would take 8 minus 1 equals 7 steps, and it would be 7n over 8 steps. So we see this pattern. We see that the coefficient of n is always going to be 1 less than the denominator of n, and the denominator of n is always going to be a power of 2. So building a formula from this until we reach until we combine all 2 groups into 1 group of n, we can actually make a formula right now, because we can keep inducting this to all the way to n until we have 1 group of n. So we can actually build a formula for this. So the formula I will explain, but it is this. So we start from m equals 1 to to m equals log 2 base 2n, and that will be n times m. Actually, it starts from m. 2 to the m. Sorry, minus 1 over 2 to the m. And if you see this, if you see how this works, it would be essentially sorry about that. If I can get rid of this, it would be essentially if you look at this, it would be n over 2 plus 3 n over 4 plus 7n over 8. So this formula actually fits it. Now you may be confused a bit. Why is log 2 to the n here? Actually, I should say lower bound, shouldn't I? Well, I don't want to confuse you guys too much. So we'll say why is this here? So we have to define a point in which we cannot do this any longer, and that's when this denominator, this is larger than n. So this has to be less than n. And why is that? Well, then after that you get if it's larger than n. The problem is you can't divide n into groups that are larger than n, because that would mean that, like, for instance, if you have 5 elements, you can't divide a group of 5 elements into let's say 6 groups, because it doesn't work, because there's more groups than there are elements. So the denominator always has to be less than n, and to ensure that the denominator is less than n, we have to make sure that the power of 2, in other words m, we have to make sure that this power of 2, 2 to the m, is always less than n. And how do we do that? Well, that basically means that the greatest power of 2 that is less than n would be less than or equal to, I should say, would be log 2 to the log 2n, because this notation basically defines the greatest power of 2 that can fit under n, I believe. Is that right, Daniel? Am I getting all this right?
Yeah, I think so.
Yeah. You can do lower bound because this is most likely not an integer, so you can actually do lower bound here, lower bound of log 2 to the n, which is why we want to stop when m reaches log 2 to the base 2n. Yes. So, oh yeah. So let's finish this up. So, why is this number why is this number, why is this less than n minus 1 over 2? And to do this, let's move to a new area. All right. Okay, so to do this, let's think for a bit. So if you essentially, if you have n times n minus 1 over 2, it's going to include all the digits from 1 plus 2 plus 3 all the way to n minus 1. Now if you have the notation of this, I'm not going to write it out, but you should probably have already memorized it because it is very important. If you have a notation like this, that basically means let's see, what does that mean? That would mean so it's n over 2. Now what's interesting is that n over 2, since we're only dealing with integers here, because as I said, it approximates. It's going to be off by 1 or 2, but essentially, if you go n over 2 or the lower bound to be exact, it's going to be included in here, because assuming that n isn't two elements, which is trivial. It's a trivial case, hopefully. But if assuming n isn't 2 elements, it's multiple elements, then n over 2 is definitely going to be in this sequence. So plus 3n over 4. Now, assuming that n isn't a trivial, it's also going to be in this sequence. It's all going to be included in this sequence until we approach the last giant merging together of sequences, like the last sequence merge, and that's when we have two sequences merging into one. That's the case where n over 2 merges into n, and that takes exactly n minus 1 steps, and n minus 1, as you can see, is included in here. So all the elements of this sequence is included in n minus 1 over 2, and we have extra. We have 1, and there are going to be a lot more elements in this sequence. Hopefully you have enough common sense to see that, because, oh yeah, it's relatively evident, and this is not a formal math video, so I'm not going to go into great depth proving every single little thing, but hopefully you see that all these elements that are found within here, so all this is also in here. But this one has extra. This one has extra elements. So this has extra elements. So this has extra elements. That means that n minus 1 over 2 will always be greater than this thing. Will always be less than that. So which is why if you're ever sorting or alphabetizing books, you should always take them in pairs, merge the pairs together by using this method, merge those groups together, merge them. It's going to be much easier than using the conventional method of, okay, let's go through, see which one's the least, the which one starts with A, which one's the least number. It's going to be much better than that. So hopefully you found this video helpful. We might do a video on the heap method, but actually I want to show you guys one last thing. If you guys want to see this, if you guys see this, okay, ignore the background stuff, ignore that virus. You guys can see the simulation, hopefully. And you will see that if this is a group that is in a random initial order. So if these are various methods. I believe selection is the one, or maybe insertion. But either way, if we run the simulation, this is how fast a computer would sort these elements. So here's the merge method right here. And I want you to pay close attention to the merge and heap. Heap finishes slightly earlier. Quick and quick 3 finish slightly before merge. And as you can see, insertion and selection are just slow-mo, you know. They aren't doing much. They're not going to help you much if you're sorting books or something. So if we can try it with 50, greater data set. And if we do it, you can, here's the merge going. Insertion's going pretty slow. Not entirely sure what quick and quick 3 are, but yeah, not entirely sure what bubble and shell are. But as you can see, they're clearly inferior to merge and heap. So I hope you found that helpful. And if you're interested, you should tune in to our next video. So see ya. Hi guys, you're watching the new channel Cyclic Squares. I'm Zong.
And I'm Daniel.
And every Sunday we release new videos about fun math topics. As we used to be students ourselves, we know what other students have a lack of understanding in, and we plan to accomplish